Welcome to OpenHW TV Season 2, Episode 6. Today's episode is focused on the Core 5 Extensions Interface project that we have underway within the OpenHW Group ecosystem. And joining me today for the episode will be Tim Whitfield, Chief of Engineering with Imagination Technologies, Davide Schiavone from our OpenHW Group engineering staff. He's our Director of Engineering of the Core's Task Group, to talk about the motivations behind the Core 5 Extension Interface project. Trefor Southwell, who's a Senior Director of Hardware Engineering with Imagination Technologies, and Trefor will talk to us about the overall project structure and roadmap. And finally, Jeremy Bennett, CEO from Embecosm, will join us to talk about the software implications of adding custom extensions to a RISC-V core, namely in our Core 5 family. But before we get into the details of the episode, I'll provide a brief overview of the OpenHW Group and the ecosystem. So the OpenHW Group is a nonprofit global organization registered in Canada and driven by its members and individual contributors, where hardware and software engineers can collaborate on the development of open source artifacts, and in particular, the IP, software tools, and overall verification infrastructure, with the initial projects being our Core 5 family of open source RISC-V cores. So this is an international footprint of developers from North America, Europe, and Asia. We focus on industry quality, commercial tools-based development environments to create these open source artifacts in line with industry best practices. And we have very, very strong support from industry and academia, as well as individual contributors worldwide. We're currently sitting at 71 plus members and partners. And on this slide, you can see the breadth of the industry members and the ecosystem, very large systems companies and chip companies, smaller organizations on the tool side, on the system side, quite a breadth of representation across the industry. And also on the academic side, very, very strong research and academic institutions from around the world participating in these projects. And on the partner ecosystem side, a very, very strong roster of partners helping us curate these open source artifacts. The way that the OpenHW Group is structured is through a series of working groups and task groups, all of which report into our board of directors. So we have a technical working group, which is effectively the R&D of the organization, if you will. And under the technical working group, there are 4 task groups looking after the cores themselves, the verification work associated with those cores, software tool chain and operating system and IDEs to support those cores, and then hardware implementations, both in the form of FPGA as well as SoCs and development kit boards that we will supply into the ecosystem. And together with the open hardware engineering staff that we have within the organization, we collaborate with the contributing members, engineers from our contributing members to create these projects. And there are a number of OpenHW Group projects underway. More than a dozen or so projects currently in the ecosystem, ranging from the RTL for the cores themselves to verification, GCC LLVM compilers, FPGA implementations, SoC implementations, and so on. And one of those projects is, in fact, the Core 5 Extensions Interface project that we'll be talking about today. So this slide shows the roadmap of our Core 5 cores, and it's really grown since the original contributions from the team at ETH Zurich, where we have a number of variants of the original RISC-V core, which is the CVE4 32-bit 4-stage embedded class core, with extensions for security, extensions for performance. We're verifying the full pulp extensions, namely hardware loop instructions in this work. We also have a 2-stage core that we'll be getting underway. And on the application side, the original Ariane core, we have both a 64-bit and a 32-bit implementation of that application class core in development. So a very, very healthy roadmap. And one of the aspects of RISC-V that's so interesting is, in fact, that it's an extensible instruction set architecture, and that there's a reserved instruction space where users can define their own custom instructions for custom accelerators that they want to attach to a particular core. For us, that work is being specified as part of the Core 5 extension interface project. And that's what the topic is for today's Open Hardware TV discussion. And with that, I will hand it off to Tim Whitfield, Chief of Engineering at Imagination Technologies, to talk about the motivation for Imagination and why they're here at the Open Hardware Group ecosystem. Tim, over to you.
Thanks, Rick. Hi, I'm Tim Whitfield. I'm the Chief of Engineering for Imagination Technologies. I head up a global team of around 500 engineers who are responsible for delivering all of Imagination's IP. I'm sure many of you will know Imagination as the leading supplier of GPU IP for mobile. 2020 was a really amazing year for us, and we saw significant growth across a number of markets, including autonomous, desktop, data center, consumer, as well as our more traditional mobile. In addition to mobile GPU, Imagination also has industry-leading neural network accelerator IP, and we have some Ethernet packet processing IP, and GPUs that span highly efficient applications, very low power devices, right the way through to GPU compute, which can power autonomous vehicles. For the last 18 months or so, we've been adopting RISC-V processors. We're using them as embedded processors that sit inside of our GPU IP. As you can imagine, these processors require real production quality verification and validation. We need to meet ISO 26262 functional safety requirements, and they need to be supported for the lifetime of the IP, just in the same way as our regular IP is. More generally, we share a vision for future compute platforms that is very heterogeneous. I think in order to meet the compute needs for autonomous solutions or highly constrained AI, VR, AR devices, we're going to need this mixture of compute elements. From bespoke accelerators like Imagination's own NNA and GPU, together with highly optimized CPUs, maybe some with tightly coupled accelerators or custom instructions or custom features, all of these things will be required to provide the performance required, whilst of course meeting very strict power and energy requirements for devices that are running off a battery, running on the edge. For me, solving this problem from both a hardware and a software perspective is something that I don't see any one company doing alone. It's going to require collaboration, the bringing together of technology from multiple sources. Of course, we think and believe Imagination are perfectly positioned to enable a lot of this, but part of this solution we see as coming from communities. Collaborations of both established companies like Imagination, research institutions, emerging technology companies, all these people pooling resources that are going to solve the complex problems that we need to solve. And this is one of the major motivations and the reason why we decided to join Open Hardware. The vision of enabling a heterogeneous compute platform is a shared one. We can both contribute, and Imagination can contribute and benefit from this alliance. For me, whilst the concept of open source hardware is relatively new, it's really exciting and I think growing in influence. We all know how important ecosystems are in our industry, and ecosystems are being formed around RISC-V, around open source hardware. And I think it's really important that companies, leading IP companies like Imagination, are part of shaping this exciting new world. We're here to learn and understand, to talk to other members of the Open Hardware organization, understand their motivations and why they're part of the organization. We're also here to contribute, and later in this show, my colleague Trevor will be talking a little bit more about what Imagination are doing as their first contribution to the organization. And of course, we're here to benefit. We want to be part of the ecosystem and grow with it. We want to shape and influence and of course integrate open hardware IP into our compute solutions. So I'm really excited to be part of this organization. As ever, the industry continues to evolve, and I'm really looking forward to being part of the evolution of open hardware. So thanks for listening. If you want to get in touch with me, please reach out. I'd love to talk to you more about Imagination and their participation in open hardware. Meanwhile, back to you, Rick.
Great. Thanks very much, Tim. Appreciate your support and your contributions. Now we're going to turn it over to Davide Schiavone, who's our Director of Engineering for the Course Task Group here at the OpenHW Group, and Trefor Southwell, who's a Senior Director of Hardware Engineering at Imagination Technology, to talk about the motivation behind the Core 5 extension interface project itself, as well as the overall project structure and roadmap for the Core 5 extensions. Davide?
Thanks a lot, Rick. Let me start discussing about the reasons why we are developing the CVX interface. So, as you are familiar with RISC-V, one of the crucial ideas behind this ISA is that it's customizable by design. So this attracted many users as they were willing to extend the ISA to cope with their own applications in a more efficient way. We have many examples both from industry and academia, as the XPulp extensions that have been designed to cope with higher code density and higher performance with at the edge computing algorithms for DSP and packet SIMD, or code compression that reduce the code size and close the gap between RISC-V and ARM ISA codes, binary code size. Another custom extensions that we have and are about to become standard RISC-V extensions are the bit manipulation that are about to become standard, the DSP and packet SIMD, the RFP vector for high performance applications and code size. If you're designing your own CPU, and you're familiar with custom extensions, you are probably doing hardware and software co-design and verification. So that means that you're extending your decoder to recognize the new instructions and activate the data path to compute the functions of it, verifying the new hardware, and at the same time, you're extending your compiler to translate the C code you wrote efficiently using your custom extensions. So that means that you have a deep knowledge about the CPU architecture as you are modifying for your custom extensions, and a deep knowledge about the compiler as you are probably extending GCC or LLVM. If you're basing your work on open source projects, that means that you probably have your own fork of your RISC-V IP, probably an open hardware one, and you are modifying the decoder to have your custom extensions, and periodically you need to synchronize with the main repositories to not miss any updates nor bug fixes. And the same will hold for the compiler. So you have your own fork of GCC, and you are applying patches to allow the compiler to translate your code with your custom extensions. That is really, really an effort making, and it's really time consuming. So to solve this issue, we wanted to have a way to extend both the CPU and the compiler in an agnostic way, exactly like the RISC-V ISA. The RISC-V ISA has some encoding space that are customizable, but they don't know anything about the custom extensions you are about to implement. And the same we want to do for the compilers and the CPU. So this is the reason behind the CVX interface, which is an hardware interface. So now we are talking only about the CPU that allows your RISC-V IP to offload custom instructions to your coprocessor. The RISC-V IP doesn't know anything about your custom extensions because it's agnostic. Therefore, it will recognize the instructions as illegal, and it will offload the illegal instruction to the CVX interface. On the other side, we have your of the interface, we have your coprocessor that is instead decoding your custom extension, signaling the core, hey, this instruction is mine, it's not just illegal, and it will then execute the custom extensions and reports back to the core the results so that it's stored in the register file. This is how the protocol looks like. So on the right side, we have the figures that reports the core, the accelerator decoder, and the coprocessor per se. We have the X interface, which is used by the core to offload the instructions that are recognized as illegal to the accelerator adapter, which is then checking whether this illegal instruction is a truly illegal one or it's a custom extension. If this is a custom extension, so it will raise a request to the C interface to communicate to the coprocessor that we have a new instructions available, that the coprocessor will then decode and execute. Same we can hold with the memory request. So if you want to share memory, memory resources, if the coprocessor recognizes that the custom extensions is a memory custom extensions, it will raise a request towards the CMEM interface. Then the accelerator adapter will recognize the CMEM request that will translate it to the XMEM request towards the core that will then compute the memory operations for the coprocessor within the core resources. This is not just a theoretical activity that we are doing. We're actually verifying the CVXIF interface in the RTLs that we have. So we are using the already verified CV32E40P core to leverage the CVX interface to compute single precision floating point extensions. So the floating point extensions are standard extensions. The core don't technically need to be agnostic about because they are anyway open source. But we are using them to test the PPA figures of the core when using this interface. We don't want to lose any performance, and we don't want to mess up power and area. Then we are instead extending an application class processor, the CVA6, to actually verify how the interface works with custom extensions. In this case, the custom extensions are done for security. So for security applications, the coprocessor is a secure coprocessor, and we are evaluating the interface on the application class. Finally, we will leverage the interface on the CV32E40X core. X stands for CVX, indeed. So this core is really designed to be the host, the true first host of this interface, the driver actually of this interface, because this will be the first core, RISC-V core, designed to be extended easily as its ISA. So a user can use the CV32E40X core and rely on a verified RISC-V processor, and then design their own coprocessor that will then execute the custom extensions without spending all the time in synchronizing their own version of the core with the mainline, as they can rely on the mainline without pushing any custom extensions to the OpenHW repositories. And finally, and in parallel with the RTL activities, we are also verifying the CVX interface with format specification. So thanks a lot for listening. And now let's listen to Trefor that will explain us how the project management is actually done.
Okay, thanks, Davide. So I'm just going to talk a little bit about how we're constructing the CVX interface project concept. So this project is the creation of a specification for the CVX interface between RISC-V cores and coprocessors, particularly the specification itself rather than a complete implementation. This project is led within the OpenHW cores task group. So it's obviously the specification of the processor coprocessor interface, but it should be applicable to all RISC-V cores and not just the CV cores developed within OpenHW. It leverages the RISC-V ISA encodings that are already supported, and it provides an accelerator agnostic instruction offloading method. So we have a 0.1 draft of the specification from ETH Zurich, which is available on GitHub, and this is being moved into the OpenHW Group for the further development of this project. So what are the objectives of the project? So to provide a unified accelerator interface, to decouple the development of accelerators from CPU cores, and to be able to reuse extension accelerators within different CPU cores. We'd also like to be able to share expensive accelerator units across multiple cores in a cluster, and where possible to try and minimize the overhead of using the extension interface. So there's the performance, the area, and the clock frequency. So compared to just modifying the core internally, this external interface shouldn't pose a large overhead. So in order to produce specification, we need to validate it in some ways. And our primary validation will be the implementation within the CV32E40X core. That includes support for compressed instructions. There's a potential implementation in the 64-bit CVA6 core. And that includes validating the performance and area of an external floating point unit and comparing that to an internal one that's pre-existing. Potentially using the interface for the RV32F extensions to the CV32E40P core. The project team who are working on this is obviously the OpenHW organization is coordinating the process and making sure it fits in with all the other projects. Imagination Technologies for the project management. ETH Zurich will provide the initial 0.1 draft that we spoke about, but also help to feedback throughout the development of the 0.9 draft. E06 HQ will be doing formal specifications, which will help to achieve the 1.0 draft. Embecosm, we're going to be working on the compiler for the initial extensions. Thales will be giving feedback from the CVA6 and RV64 ISA. Silicon Labs on the CV32E40X implementation itself, we're supporting this interface. And the University of Bologna exploring the X interface for the XPulp NN ISA custom extensions. So we've got lots of contributors. So how do the milestones look? So this is where we are now with a 0.1 draft. There's been lots of contributors, as you can see on the diagram. Then moving forward from 0.1 to 0.9, we'll be taking feedback from the different stakeholders. So obviously Silicon Labs, who are doing some work at the moment on the CV32E40P, EOSIS HQ, ETH, obviously, and the University of Bologna. And then we're also going to have Thales on the 64-bit side on the CVA6 RVFD extensions. And that should take us towards the end of this year to achieve a 0.9 draft. From the 0.9 draft, we are obviously gathering final feedback, and we're going to actually implement that in the CV32E40X core. So Silicon Labs will be doing a lot of that work, while the OSIS HQ will be developing a formal specification that will help to validate the interface itself, and Embecosm building the compiler for the initial extensions, and that will lead us to a 1.0 release, which is a validated interface specification. So thanks for listening, and back to you, Rick.
Thank you very much, Trefor and Davide. And finally, now we're going to hand it off to Jeremy Bennett, the CEO at Embecosm. Jeremy will talk about some of the implications from a software toolchain standpoint on custom instructions and custom extensions alongside a RISC-V core. Jeremy?
Thank you, Rick. The ability to create custom extensions easily using the Core 5 extension interface leads to a requirement for custom compiler chains, as Trevor has said earlier. We want to be able to create these as simply as possible. Compiler toolchains are a key component of the Core 5 ecosystem, with support for both GCC and Clang LLVM toolchains. In this slide, we see all the components that make up a toolchain. the compiler and assembler, the low-level utilities, the debugger, the compiler libraries to emulate missing functionality, and the standard language libraries. These are large code bases with more than 11 million lines for the GNU tools and 7.5 million for Clang LLVM. Today I'll focus on the GNU compiler toolchain, but the process is very similar for the Clang LLVM toolchain. Both GNU and Clang LLVM toolchains have a well-established technique for vendor-specific toolchains. The second field of the target triplet can be set to a named vector. So since this is an example for Core 5, we've used the word Core V. This technique can be used for vendors who wish to have their own toolchain for Core 5 extension interface custom extensions. This will lead to appropriate naming of the target commands and will also provide a C definition, allowing conditional compilation of code just for the vendor version of the toolchain. To extend the compiler for a custom Core 5 extension interface extension, we adopt an incremental approach. We first develop the assembler and linker, which can be used within C and C++ via the inline assembler. We then add compiler built-in functions. Because the compiler has full insight into the semantics, these are more efficient than inline assembly code and can dovetail with other optimization patterns. Adding compiler code generation patterns allows the instruction extensions to be generated automatically for standard C and C++ code. Finally, we can add more patterns and custom compiler passes to maximize the optimization opportunities with the instructions. And of course, throughout, we must test robustly. So let's look at this in a bit more detail. Let's start with bin utils, and we can break this process down into 3 steps. Adding the instructions to encode and decode tables, editing the assembler to make use of these new table entries, and adding linker relocations if required. Just 3 files need to be edited for the assembler and disassembler. Changes to 2 files in the opcodes library provide a detailed description of the syntax of the new instruction and add the functionality for its disassembly. The main assembly source file can then be modified to generate the code using the information from the opcodes library. For any instructions that use standard formats, this work is straightforward for an experienced software engineer. Using custom formats makes the work more complex, and a specialist might be needed. Relocations are very common in position-dependent code. Standard relocations may not be suitable for custom extensions, which may therefore require new custom relocations. For example, the standard Core 5 hardware loop extension requires a non-standard relocation for the cv.startI instruction for the field containing the start address of the loop. The linker and relocations are not easy to get right, so this is an area where a software specialist might be needed. The implementation of Core 5 extension interface extensions in GCC can be split into a number of steps. Firstly, creating a machine description of each instruction, including adding operand constraints. Secondly, creating built-ins where possible to call these instructions directly. Thirdly, adding patterns to these instruction descriptions so the compiler is able to recognize these and substitute in custom instructions as needed. Finally, modifying existing optimization passes to use the custom instruction and adding new passes as appropriate. The first 2 of these steps are fairly routine, and we can provide guidance that will allow an experienced general engineer to get started with this work. However, when we get to automated code generation, and even more with code optimization, then specialist compiler expertise is needed. Testing is central to any production quality compiler. And we distinguish between 2 types of tests. First of all, tests which check the compiler generates valid code, and secondly, tests which check that the generated code executes as expected. Failures when compiling can be very annoying, but these failures occur before code is generated, and ultimately no harm is done. However, if we have execution failures because you've generated code that behaves incorrectly, we have bugs. And if that code has been placed in the ROM of an ASIC, it can be very expensive to fix. So ensuring there are no execution failures is a critical part of testing. The GNU tools have a comprehensive set of regression tests of both the compiler and correct execution of the generated code. LLVM has a comprehensive set of compiler tests, but its execution test suite is only suitable for larger processors with an operating system where it can run natively. Fortunately, a large proportion of the GNU execution tests, notably for GCC and GDB, can be used with LLVM. This is standard practice for commercial-grade compiler development and is thus used for all Core 5 toolchains. Users may want to upstream Core 5 extension interface extensions to the official GNU toolchains. There is a process that is well established for upstreaming vendor-specific versions of toolchains using the middle field of the target triplet as I described earlier. For example, on this slide, we show the generic upstream MIPS toolchain and two upstream manufacturer-specific versions for Imagination Technologies and MTI. Things are slightly harder for Core 5 because the GNU linker supports all GNU targets simultaneously. And with RISC-V and Core 5, we may have multiple vendor-specific toolchains upstream, and vendor-specific relocations may collide. There are not sufficient vendor-specific relocations for each vendor to have their own set, and in any case, this would need a central authority controlling allocation. Work is currently in progress by RISC-V International to adopt a generic solution to this problem. So far, I've described how to modify the existing Core 5 toolchain to support Core 5 extension interface extensions. This is fine for small instruction set extensions, but does not scale well. And I've also not addressed the question of how you simulate these changes, allowing you to test and evaluate toolchains pre-silicon. There is a more scalable way. CGen is a long-established GNU toolchain which generates the assembler, disassembler, and simulator from a formal specification of the architecture syntax and semantics in Scheme. We've used this with one customer to give a 24-hour turnaround from instruction specification to simulator and toolchain. And LLVM has a similar tool, TableGen, which is at the heart of its compiler. It's used as standard to generate the integrated assembler and disassembler. It does not automatically generate a simulator, but can be used to provide the framework for a handwritten simulator. I am the chair of the software task group for the OpenHW Group, and I'm also chief executive of Embecosm. But this work has been a joint project for the OpenHW Group, and a major one at that, with many engineers involved. I'd like to thank my colleagues at Thales, the University of Tübingen, the University of Bologna, and all my colleagues at Embecosm for the effort that has made this work possible. Thank you. Back to you, Rick.
Thank you very much, Jeremy. We'll now turn it over to live Q&A and invite your questions from the attendees. We will take questions from the chat window, as well as questions that many of you gave us during the registration process. Some good questions came in. So first off, we had an attendee ask about, will this recording be available for viewing later? All of the OpenHW, short answer is yes. All of the OpenHW TV episodes from season 1 last year and this year in season 2 are available under the OpenHW TV tab on openhwgroup.org on our website. That takes you to the YouTube channel for all the episodes, as well as Youku in China. So there's lots of access to the content. Bunch of questions. I'll take a couple that came in on the attendee registration form first, because they're sort of generic. One about, okay, great, what's this going to do to performance between a say like the FPU, a built-in FPU versus an external FPU. So a discussion around the performance impact of this kind of an interface to get out to an accelerator. So maybe Davide and Trefor, you guys want to take a stab at that?
Hi, Rick. Yes, I can reply to this. So the spec is really new, and activities ongoing are really started a few weeks ago, maybe a couple of months ago. So the very first task that we are doing with ETH Zurich is exactly replying to this question: what's the impact in performance, area, and power between the, let's say, the old way of using the FPU in the CV3240p and what's the impact with the CVX interface? Of course, we are, as Trefor showed during his presentation, we are using exactly this experiment to adjust the spec in case we lose performance or if we lack any of the signals in the spec, if the spec is not complete and so on. So we are in the upper case R and phase of the stage of the work here. We are doing research to exactly reply to this answer. We expect no difference in terms of performance. So the spec is a protocol. The way you implement the protocol is will answer mostly these questions. If you want to have an FPU with a single cycle addition and a 2-cycle multiplications, and the protocol isn't impacting the offloading of the instruction, if you are designing it properly, in theory you don't have any performance loss. And this will be the first part of the experiment with ETH Zurich. And the second one will be like, okay, but once you're offloading the instruction, why don't you have the coprocessor executing instruction in a out of order fashion? In that case, of course, we expect an increase in area, but also in performance.
Thanks, Davide. Trefor, do you have anything you want to add to that, or is that good?
Yeah, obviously we've planned this in as part of the project, and it's under discussion to look more at the performance. And a lot of it depends on what you want to do with the interface as well. You know, you're not going to be able to do everything with no performance impact on every conceivable CPU, but hopefully we can get the most useful cases for people extending the CPU at a good performance as part of this work.
Right. So healthy trade-off. And as Davide said, the project is both the specification itself of the protocol, and then clearly there will be different performance impacts depending on what your implementation looks like of that spec. And within the OpenHW Group, we will have external coprocessor blocks, accelerators that implement this spec. And clearly, as an ecosystem, we will try to maximize the performance that you can get out of that. In some instances, maybe there'll be an area penalty for that, but it depends on the compromise you want to make for your work. Okay. One of the other questions was, it sounds like all the talks about the 32-bit family. What about the CVA6? Is the CVA6, if you will, an equal citizen from a 64-bit implementation in the CV extension, Core 5 extension interface project? So Trevor, you want to take that one first?
Yeah, so as you saw from the slides I presented, that the CVA6 is also running in parallel and giving feedback on the extension interface. We didn't want to gate the project based on that because we weren't sure where it would lead to, but the idea is to make sure we take account of the 64-bit cores as well, and there's nothing in the specification that would prevent them from working with this interface. Right.
Okay, so we'll come back to more hardware-related questions, but we've got a few software-related questions that came in registration as well. So Jeremy, over to you. One of the questions in particular, you sort of addressed in your talk, but maybe you can add a little more color to this with. Now, geez, I lost the question. Yeah, is there excuse me, is there an effective way to have a standard tool chain that can be easily extendable with custom accelerators and custom extensions? And you address this a little bit, but maybe talk a little bit more about the work.
So in terms of having a standard tool chain that can magically pick up the extensions, it's been the holy grail of compiler work since before I was born. So that isn't there, but what we're trying to do is give you a practical engineering solution. So tools like CGen actually automate a lot of the low-level grind, and some aspects of modern compilers can be not automated, but you can give a recipe that a professional software engineer can follow to say these are the files you need to change. And particularly if you stick to standard RISC-V format instructions, that's not difficult to do. But we are still at the stage where once you get to the internals of serious code generation and optimization, that is a specialist discipline, and no one yet has automated that. And I have some of my colleagues here at Embecosm working on, can you use AI to do this? It's something I've been working on for a decade, and AI can help, but it doesn't get around the basic problem that optimization is still a hand engineering job. And so that bit of the compiler work for the time being will be manual, but everything else, we'll provide an application note and an example that will show you how to do this, and you can take it as far as it goes, but then you'll need to bring in an expert to get the final step.
Very good. And so that, I mean, that's in keeping in general with all of the things that, all of the projects that are underway within the open hardware ecosystem. Everything that we do is open source, and you can take and use. Ideally, we'd like you to contribute back. That's how open source projects work and survive. But everything that we do is open source along the way. And that comes to another question about, is the CVXIF spec publicly available? And yes, if you go, it's just been transferred into the OpenHW Group repos from the team at ETH. So if you go to our GitHub repos, just search OpenHW Group and it'll pop up real quick. And look for the CVXIF repo. You'll see the work that's underway there. And the task groups that are working on the spec will continue to publish, .revs as we move from, as Trefor showed, as we move from .1 to .9. And in fact, in the chat window, thank you, Davide. Davide has just posted the actual link to the GitHub repo, so you should be able to go and get it there. So we had a bunch of questions in the registration list that's related to the next one here about sharing an accelerator. What do we do about coherency? Can the CVXIF accelerator be shared amongst multiple cores or hearts in an SMP type setting? So who would like to tackle that one first?
I can try to answer this question. So a very good question first. This is actually related also to another question, which is what is the difference with the Rocket chip interface, and that we are trying, still in the phase of defining though, but we are trying to have a complete memory operation model, which is a little bit different from what Rocket does indeed. And so the coprocessor should be able to raise exceptions, should be able to have their own memory port, should have their own, or can offload to the core, to the CPU, the memory requests. Of course, all of these flavors have a different impact in the memory subsystem, because if now your coprocessor is a master of the bus, then if you have caches attached, you need to have a cache that is serving two masters at the same time, or maybe two different, if you have it shared, or if you have it private caches for both the entities, then you need to implement in the bus side all the cache coherent protocol. But they are a little bit outside of the scope, because these things are part of the memory subsystem environment rather than this spec. What this spec is trying to solve is how to treat a RISC-V instruction that is seen as illegal. And this is also the other difference with the Rocket chip interface, which is, let's say, not forcing the core or not allowing the core to be agnostic. So when a core fetches an instruction and recognizes it as illegal because it's a custom extension, it will offload to the coprocessor. And then it's the coprocessor is decoding the instruction, fetching or doing other stuff, either with the memory or it's with its own data path and stuff like that. So this is what the interface is trying to solve, is the offloading mechanism plus memory, defining how the coprocessor behaves memory-wise for what side of the CPU. So from the CPU plus coprocessor as a unique device towards memory, it will be treated like any other multi-core system. This is at least what we are trying to achieve now. And if we'll figure it out that there are limitations in the spec because maybe you need to specify something else, we will add it to the spec. So actually, thanks for the question. And if you see a limitation on this kind of system with the spec we let's say we rectified so far, we didn't rectify, we wrote so far, just open an issue on the link I just provided in the chat, and we will try to solve the question there.
All right, so thank you, Davide. Another question really around sort of multi-core and heterogeneous cores that I'll throw over to you, Tim. You talked about a sort of a shared vision of systems being comprised of heterogeneous cores and clusters. What attracted you to this ecosystem to try to help work on these kinds of problems, the Core 5 extension interface as an example, and how you might see that work impacting or benefiting the team there at Imagination?
Thanks, Rick. Yeah, I mean, I talked a lot in the video about some of the motivations. I mean, I think there's a sort of holy grail of trying to create an environment where people can rapidly model, develop heterogeneous compute platforms. So, one of the questions today was around, is an accelerator IP or memory mapped accelerator better than custom instructions or better than a tightly coupled accelerator in a CPU pipeline? These are the problems that people want to solve, and it's not just CPU, it's specialist NNA compute, it's graphics compute, and the people who need rapid answers to these questions are developers, right? Systems developers, software developers who have a bunch of complex algorithms, often very proprietary to themselves, that they want to go and model on a platform and understand and answer those questions. Where do I best deploy based on the compute that I have available? So I think that is an incredibly complex problem to solve, and one that lots of people have been trying to do for a long time. And as I said in the video, I don't think any one company can solve all of that problem. It's going to take different specialisms in software and hardware and system design and memory bandwidth and all that kind of thing to solve that. And this is one way of doing that, right? So being part of open hardware gives Imagination access to, I guess, sort of an ecosystem of partners and friendly people who we can innovate with and co-develop with, and still gives us that opportunity to go then take some of that and go and build things that are absolutely the right commercial products for our customers. So I think that's quite a long-winded way of saying of answering your question, but hopefully there was some insight in there somewhere.
Well, I'm sure there was somewhere. Thanks, Tim. So we got started a little late. I'm very respectful of everyone's time. Sorry, but I think we'll extend it past the top of the hour here a little bit. If you can stay on for a few minutes, that's great. If not, thank you for joining us. There's a few questions around, hey, wait a minute, what do you mean we're going to fire this thing up based on detecting an illegal instruction? So there's a couple of questions around illegal instructions. And what happens if a real illegal instruction shows up? What do you know, where's that dealt with? Is it the external processor, since the core is kicking out, illegal instructions to somebody else? And then what happens from a security standpoint in terms of how illegal instructions are dispatched to an external core, and the internal core confirming that that is really an illegal instruction or not. So what are our thoughts around how to deal with that in the specification, the protocol spec? And Trefor or Davide, I would imagine that one of you wants to take that, or maybe nobody wants to take that. But
I don't want to be
anyway.
I don't want to be the talkative one. So if Trefor does want to reply, I'll let him do it. Otherwise, I can try to solve the issue.
Well, I think you kind of showed it on your diagram in the talk there, by the looks of it, that there's obviously an accelerator adapter, and that will detect if the instruction is illegal and raise it as a real illegal, or pass it on to the interconnect, which then allows you to address multiple co-processors. I don't know if you want to elaborate on that, David.
Yeah, basically, I don't agree with the single point of attack, because once you synthesize the RTL, it's the same. Meaning that when you have an instruction and you implement a decoder, you can imagine parallel logic checking whether this guy is an instruction. And if this is not an instruction that is legal, or if this is a legal instruction, you basically have an or an and, depending on the way you implement it. And your core finally says, okay, this is an illegal instruction, and this will be a single point of attack, right? The and or the or of all of these guys. Now what we are doing is splitting literally by two parts the decoder. The RISC-V standards, we put it here, and the other one, the custom one, we put it in the coprocessor, and we say, okay, I think this is illegal. This guy will say again, I think this is illegal, and then if we both things they are illegal, the instruction is truly illegal. And if you have multiple of these guys, because we have multiple pre-decoders, as the diagram showed, it will be the same. It will be a tree of AND gates, and eventually you will have a single illegal flag anyway. Either you implement it in a single module or in different ones. Once you have the netlist with logic gates, you have one wire that carries the information.
All right, good, very good. Thanks, Davide. So there's a final question here, and then we'll wrap it up around what's the aim of the project in terms of what we're trying to standardize with this interface, actual hardware implementations or just the API or so on. And really the answer is yes, all of the above. Protocol spec, implementations of that protocol spec in real accelerators that hang off the family of Core 5 cores. As Jeremy showed, the tool chain that supports the standard Core 5 cores with guidance on how to fork the tool chain and modify that for your own custom extensions and accelerators, and to really build an ecosystem from the RTL, the verification work as well, and the software toolchain flow to support what, as I said at the outset, arguably one of the most interesting things about the RISC-V ISA is the fact that it's a modular ISA and an extensible ISA. Making it easier to provide those extensions is what this effort is about, from specification to implementation to software tool, to verification, to software toolchain, all the way along. So with that, I'd like to thank the speakers for their efforts in presenting this to you today. If the Core 5 extension interface specification project and implementations are of interest to you, please join us at the OpenHW Group. You certainly follow us on our social channels on LinkedIn and on Twitter. And by all means, pay attention to the GitHub repos, ask your questions there. And if you really want to help drive this activity, become a member and contribute. So thanks everyone. And wherever your day is, I hope it's a good one. Bye-bye.